Okay, so for today, I wanted to talk a bit more about principal component analysis because that's really a workhorse that we use in high-dimensional statistics. And while it's sort of roughly probably clear of what's happening in there and why it works, the details might not be so obvious. At least I've tried to write it down before and noticed, yeah, once you try to write down the math, it becomes non-obvious. Or maybe it was only non-obvious to me because it took me a while to figure out how to correctly write it down. And now that I managed, I want to show this to you. But before, let's just remind us of where we are now with our data and why we use this PCA. So I use the same data as we have used last time and just load this count matrix, translate to fractions by dividing by the column sums and do our log transformation with this pseudo count, get the most variable genes there, and then in order to do the PCA, the first thing we always do is we take our expression matrix and we subtract from each gene the row means. What we want is that each gene is centered in the sense that it has mean 0. Sometimes the PCA function does this automatically, but I want to do this explicitly. So here you can now see how the expression is centered to mean 0. And if I calculated the row means, you see each gene has a mean of actually 0. It's slightly, well, you know, this is just numerically uncertain. 10 to the minus 18 means 0 because it's sort of the smallest part we can do. I should say, our server where I put the course material is currently down. The spare processor should arrive tomorrow when I can put it up again. But for the moment, I have it here, so I upload this stuff afterwards. So another thing is at the moment, each gene has different standard deviations. Some genes have a lot of standard deviations, others have much smaller ones. And what we actually want, or what we might want, is that each gene has the same chance to influence our PCA. And because of this, I standardize the genes. That means I divide each row of my matrix by its standard deviation so that afterwards all the genes have mean 0 and standard deviation 1, which we call a standardized variate. And this means that they all sort of vary about the same and go in with the same input. It's always a bit the question whether this really makes sense to standardize, and maybe we want the genes which vary a lot to have more influence on our PCA, because they do change more. Because when they do change more, maybe they are more important biologically. It's only from practical purposes, usually the results become better if you do this standardization. So for the moment, I simply do that. Now I calculate my PCA by giving it into this IRBA function, and we will later have to talk about what this IRBA PRCOM function actually does internally. But for now, it just gives us the first 20 principal components. And if you look at what this thing, the output of this IRBA thing is here a list of stuff, which tells us we haven't scaled the things, we haven't centered the things. Actually, I could tell it explicitly. Don't scale, don't center, because we've already done this manually. And if I do it like this, I can now see it doesn't scale, it hasn't centered, and it now produces us two output variables, one matrix called X and one matrix called rotation. And then this list of standard deviations. The rotation matrix has one row for each gene and the other one for, let me just quickly show you how these two matrices look like. This is the first, this is the X thing, which assigns to each cell its principal component, so 20 values, and the rotation matrix does the same, assigning to each gene principal components. So in that sense, what we have achieved now is that the genes that before each cell was described by 1,000 highly variable genes, and now we compress this down to 20 principal components, which is the dimension reduction we wanted, that we now have have information compressed into much fewer numbers. And the way how we do this is, of course, that we say each gene's principal component is now a linear combination of the individual genes' expressions weighted by these weighting factors, which tell you if you want to calculate the first principal component, multiply the expression of each gene after standardization with these weights here in order to get the first PC. So in other words, we can ask here we can look here at these first PCs, and for example, now take the first principal component and ask which one has the highest and which one has the lowest influence. So if I sort them, when I see the genes which have strong negative influence and the genes which have strong positive influence, and if I plot them in this sorted order, then you can see how there is a small number of maybe 50 genes or so which have a strong negative influence. So they are below zero, and another 50 which have a strong positive influence, and then a big chunk of a few 900 or so genes which have hardly any influence. One might probably put them completely to zero to get nothing. This is why if you want to know what kind of biology this first principal component captures, we might want to inspect these top genes and the bottom genes here and use them. And that's what we do here. And what we get out is now this matrix X, which summarizes our data in a much reduced thing, because now for each cell we now only have 20 numbers. And of course we can undo this. I can take just to see how the values in rotation actually make up the PCA$X. I have said that each principal component we calculate by taking the weights according to this rotation matrix, which we also call loadings, and form a linear combination to do this. And of course, you can write this as a matrix multiplication. So here I take my expression matrix with the expressions of the individual genes and calculate for every cell. I multiply the expression of the individual genes with the corresponding principal components to get the cell's PCs. And overall, I multiply now this matrix with that matrix, and then I get here the PCX matrix. And as you can see, the two matrices are the same. So in the end, what our principal component does, it finds this rotation matrix such that we get here a matrix X that is optimal in a certain manner, and I will come in a moment to in which sense this X is optimal. And of course, I can also undo this, because now with PCA$rotation, we will see later that it's, well, as the name already suggests, it's a rotation matrix. That means the columns of this matrix are all length 1 vectors, unit vectors of length 1, and they are all orthogonal to each other. So the scalar product of any two columns in the rotation matrix is 0. So it can easily be seen by taking what rotation matrix and multiplying it with its own transpose. What this does, it multiplies each column of the rotation matrix with every other column. And then you can see here how all the entries are nearly 0, except for the diagonal, which is 1, which is how you recognize a rotation matrix. Rotation matrix because, of course, if you go in with a system of basis vectors, which are all orthogonal to each other, when they get projected onto the column vectors, which are still orthogonal to each other, so we know the whole thing is a rotation. It might also be a rotation with a flip, so we don't make this difference, but with the determinant of this thing should be 1. So, as it's a rotation, we can undo the rotation. A rotation matrix can be inverted by transposing it. So if I multiply now my principal component scores with a rotation matrix, then I get back the original expression matrix. But I won't get back the original expression matrix perfectly, but only imperfectly, because my rotation matrix was not a full rotation matrix, but is truncated. I only had the first 20 column of these rotation matrices, and the rest is missing. And this is why the undoing of a rotation costs us information loss, and we have now much less. And the thing doesn't agree as well anymore. So let's quickly compare how well we can reconstruct a random cell. Let's take this cell number 1, 2, 3 here, and take the centered expression of all the genes before and afterwards. Each point is a gene, and now you see the actual expression of a gene on the x-axis, centered and scaled, or standardized, on the y-axis the reconstruction. And you can see it sort of works with reconstruction, but it's not great. But of course, we have reduced our data from 20,000 dimensions to only 20 dimensions. And as we've seen in the lectures before, this is enough to identify which cells are the same cell types and which aren't, and in order to bring the cell in order and see trajectories, etc. Still, to make this look a little bit better, we could undo the standardization. So on the x-axis, I will now plot the original expression values, the log normalized ones. And on the y-axis, I do the same. So I multiply again by the standard deviation and add the rho means that I've subtracted earlier from it. And now it looks actually quite decently correlated. But that's cheating a bit, because it's mainly correlated because I added these rho means, and they make it look nice because the rho means are very different from gene to gene. I could also say, in the end, we never compare one gene with the next gene anyway, because in practice, what we rather do is compare a given gene across cells and asking which gene is in which cells is which gene high, in which cell is this gene low. So I might take some gene, let's say the 13th gene with the 13th highest variance, and just plot it. And now again, I plot here on the x-axis the original expression of a gene, and on the y-axis I plot the PCA. And still, maybe if I take the first view, we get a good correlation, but already after the second, third, fourth, the correlation isn't that great. Actually, I was a bit surprised myself that it is so mediocre. But this is what we always start with, and still it works well. But it should remind us that we should use this PCA really only as a measure to see how similar two cells are, and then use this for our UMAP plot, but not for something else, where we then go back to the original data. So what I now wanted to do before I go back is to explore a bit math, because all the stuff I've just told you about how the PCA is calculated might sound roughly familiar to most of you, but the details might be a bit hazy, and usually you don't find the details fleshed out well. There's always some vague talk about whether there's some eigendecomposition involved in it, and I thought it might be useful to do this explicitly. So I sat down and wrote this up, and now I will show you how this here looks like. And instead of now going through here my write-up, I will just write it on the board and only use this here to cheat, to look up occasionally in case I lose the track. But let's see what we here do. Where do I start? I start here at the bottom. And what I will also do, in case somebody should look at this thing later, then I this here so I can sort of record the board. So we start off with our matrix Y. That one is wet. And this data matrix Y has with columns yi. So I will use indices in a certain way. I will always be the index, will always be indices for cells. And so here it was column index of this matrix. And I will use J for the row index, which are here the genes. Or if we consider it more generally, then these are the objects and these are the features. And what we now want to do is we want to reduce these yi, which come from a high dimensional space, some Rn, so this is the number of genes, and we want to reduce this to a much smaller space. And the way how we can think about this is we are now looking for the optimal linear transformation, which reduces this down here to want to reduce to an xi element Rk, such that information loss is minimal. And we want to do this in a linear transformation. Later, in later lectures, we will realize that we can gain a lot by deviating from the idea that it should be linear and looking for a nonlinear transformation. But if you reduce ourselves to a linear transformation, what we're essentially doing is projecting our feature space in a subspace. So this means look for a subspace S of this feature space, such that if we project the yi into the subspace, then we don't lose too much information. So we call P is the projection operator into the subspace. So I decompose the yi into this here, which is the projection of yi into the subspace, plus, well, whatever is left here, some remainder. And this, of course, means the whole space, the R to the n, is now decomposed in the subspace and a space orthogonal to it. And where the space orthogonal, this is the kernel of the projection operator. So that's what we do here. That's what we are looking for. We are looking for a projection operator so that this is minimal. So we want that the sum, that these, so the projection loss, or the, that is this part which we lose. We start in with a vector yi, and then we get this vector, which is projected into it. Maybe I should make a little drawing. So let's say this here is S, and this is my yi. And what I now do is I project it here onto Pyi. And this here, what I have up here is delta yi. And I want to find such a subspace that if I project the matrices down into the subspace, I don't lose too much of this thing, and and this thing stays as big as possible. So my projection loss is, of course, this part which I have here, which is delta yi, or yi minus Pyi. And to say what the loss is, let's say I add this up over all my cells and say the sum of all these things squared should be minimal. So this is the length of the vector that I'm missing here, and I want to minimize this. Now, because this here is a right angle, I can use Pythagoras and can say this part that I'm losing here, that is the original length minus the projected length. And this should be minimized, which means that we want to maximize that, because this here, this is constant. This is just our data. This is the total variance of the data, just the sums of squares of all our data values. And this here is our projection, so we want to find the projection that maximizes this thing. And in order to do that, what we want to find is a projection operator that defines the subspace. And to do this, we now write a basis for our subspace, which I call P1, P2, pk. So these are the basis vectors of the subspace S into which we project. And now, with these basis vectors, I can now calculate this thing. So the loss is the sum over all our cells of, no, not the loss, this is the gain. So, so this thing that I want to maximize here. And now I can think about how do I measure the length of the projected vector. And you can imagine if you have this data vector and the feature vector and we project it into our subspace, then we can try to expand this projected vector in the basis for S, which means that we have to look at each element here. S is 1, 2. Now, what did I always use? Yeah, I think I use S. Okay. And now I can say this here. So this here is the scalar product of this basis vector with our data vector. So if we multiply a scalar vector, so of course this basis is orthonormal, so all these p's are length 1 and they are orthogonal to each other, which means I can just find a basis representation of this vector by projecting it onto the basis of P. So for example, if this might be now the basis vectors of P, P1, P2, then I can now take this vector P, this projected vector and expand it in this basis. And then of course, if I multiply this matrix with that one, I project this matrix on the projected vector on this basis or on that basis, and then I get the component in this direction or in that direction. As you usually do it when you have a matrix and you want to expand it in a basis, you project the vector onto one basis vector, onto the other basis vector, and then you get the coefficients. And of course, if we square these coefficients and add them up, then we use Pythagoras, and now we get this thing. So this is how we can write down the basis of this projected vector. I like to write my scalar product in this manner as I've written it here, by writing the left vector as a transpose, which means the vector has been changed from a row vector, from a column vector to a row vector. So I multiply row vector by column vector, and that of course gives you a scalar. You might recognize this is what in physics we usually do when we write something as a cat and then a bra. Or no, in that case, this would be the bra and this the cat. I do it the other way around otherwise. So, and now I have found this, and what I now do is I ask myself, how do I optimize this thing? Which part was missing? Yes. So we see here that this is now, that here I've now explained why it was, and this thing I can expand in two ways. I can say this is I and S, and I can now say I write this as, let me see if I do it correctly, PS TYI, and now because here I have a square, so I should write this thing twice. I write this thing and I write it another one, and the other one I write as a transpose because it's a scalar, and if I transpose a scalar, it's still the same. So I can write this now as PST YI. So what we now have here, here's my T. What I now have here in the middle, this is now the projection operator together with that sum sign. Because, you see, that's what it does. It projects an incoming vector that comes in from the right, is projected onto one of the basis vectors. Then I get the length in the basis vector, and I multiply it again by this basis vectors to reconstruct it. So in a way, that thing here, again, also here now write that the projection of I on Y is the sum over all Vs, projection vector S transpose Yi. Just to remind you how a projection actually works. That's how you project a vector onto a space spanned by this basis. And provided the basis vectors are all orthogonal, otherwise it doesn't work. So, and now that we have this, so I've explained what we've done here. I've projected on here, and then I multiply with that, and then I get, of course, the norm of a projection, but I can also expand this another way around. Namely, which way do I now do this? PS, T, YS, YIT, T. Now I've put the Y in the middle and the P's on the outside. So I've turned the thing around by saying I have this operator in the middle, and the trick is now to recognize that, let's write this up here, that if we take these things here, we can build up our whole data matrix Y transposed with itself. It takes a bit of looking at it, that this is the same, but you can imagine, you take, remember these are the column vectors, the Y's are the row vectors of a matrix, but we write them here as column vectors. I have done this a bit unclear. It took me also a bit yesterday to realize that this is exactly the full matrix here. But but you can, anybody has, do you believe me this, or should we look at it in detail? Why the data matrix multiplied by itself gives you, can also be written like this. So what we have here is essentially the same as the sum of ES T I Y T Y P S. What we now have here is what we call a quadratic form. We have this operator in the middle, this YTY, which is just our big data matrix multiplied with itself, and we multiplied the projection operator from the left and from the right onto it. And we can understand this as some quadratic form which takes this vector and calculates a scalar out of it. And as you might know, quadratic forms have this thing, usually they always admit an eigendecomposition. That's the way how a quadratic form works. A quadratic form can always be written as a symmetric matrix. This is a symmetric matrix where we multiply a vector from both sides to it, and then you can write, and then you get this thing here. So what we want is a eigendecomposition of this thing. So what we now do is we introduce an eigendecomposition, because this is how it's the easiest to write a quadratic form. Position of YTY. And we have the eigenvectors. Now how do I call them? I call them U L. So S here is the directions of projection basis components, and L lists the eigenvectors. And we will see in a moment that the U's and the P's turn out to be the same, or should be the same, but we don't know this yet. The moment we simply say we have eigenvectors UL and eigenvalues, let's call them lambda L, so that YTY applied to an eigenvector UL gives us lambda L UL. And this now means, of course, that, and now we can calculate what our Q is. So decompose. Now let's ask, what should we put for the first, what would be a good basis vector for the projection? So we now want to choose a basis vector for our projection to find the basis vector which maximizes this quadratic form. So just as a reminder, we wanted to maximize this here. So now let's choose P1. And we expand it in eigenbasis of YTY. So P1 is, we go through the eigenbasis, take the eigenvectors, and say there should be some coefficient. And if we do this, we can now ask, what is this Q of P1? So this quadratic form on it, which should of course be, which then will be we know that Q of UL is of course lambda L, because that's how we define this here. That's the whole point of writing a quadratic form in its eigenbasis, that you can then say, if you have a matrix, then you can construct it that way. So this is then the lambda L, rho 1L, lambda L, alt 9. I wanted to write this down here. So this is then the sum over all the eigenvectors, rho 1L, lambda L. So this is what happens if we, just to recap where we are, we have our subspace S into which we want to project, and we now want to find a good basis for this subspace. And we say, okay, let's take one first basis vector and try to find something for this first basis vector. And for this, of course, we see what does this basis vector, what happens if I choose this basis vector and multiply it from this side with this data thing? What does our data YTY matrix make of it? And what it will do depends here on this one. And obviously, the bigger we make these rows, the better. But we have our constraint that we want to make an orthonormal basis. So we want to say that the sum of the coefficient should add up to 1. Otherwise, it's not an orthogonal basis. So we have to ask, how can we put different weight into the different components such that we all add up to 1, such that this here becomes maximal. And then it's, of course, easy to see. We have to take the one with the largest eigenvalues to put it in front here. So we want to choose, so this thing is maximal for Q11 is 1 and rho 1L is 0 for L greater than 1. So we choose the vector which has a 1 in the first component and 0 always everywhere else, because when we follow our constraint and the 1 stands in front of the biggest eigenvalue. So of course I've forgotten to say the eigenvalues are as usual, they are ordered with lambda 1 is the biggest, lambda 2 is the next, and so on till we have the last eigenvector lambda k. Okay, n I meant. And this tells us now what we should do. We should choose as the first basis the component, a vector which puts all the weight on this first biggest eigenvalue, which of course happens if we take for this thing the top eigenvector. So we should choose, so the best choice is when that we put P1 to U1, that we simply say the first projection should be the top eigenvector of this YTY. And then if we want to find this next projection, when we can't put any weight on the first component because it should be orthogonal to the first component. So P2 is orthogonal to P1, therefore is the best choice when P2 is U2. And from all this together, we can now conclude the optimal subspace S into which we want to project our data is the one spanned by the first k eigenvectors of YTY. And this is the result. And this is the reason why in a principal component analysis you go through this eigendecomposition of YTY. Because on the first look, if you just look at it, it's not immediately obvious. Why do you have to transpose your data matrix and multiply the transpose by itself and then make an eigendecomposition of this thing? But here you see where it comes from. We ask, how much do we lose by the projection, or how much do we retain in the projections, or how big are the projected values? That's what we have here. And to do this, we have to look at this quadratic form here, where the p's are multiplied by the y's, and you can see this in two ways. You can see this as a quadratic form made by the projection operator, by the projection vectors, acting on the data vectors, or you consider it as a quadratic form made by the data vectors acting on the projection vectors. And the second one is the useful one, because it allows us to say we have to optimize this quadratic form, and for that we look at the eigendecomposition of that quadratic form, so at the eigenvectors of YTY, and say if we make our projection vectors as the top eigenvectors, then the amount of data we receive is the top eigenvalues. We can then also see from this that when the retained information or sum of squares is when, what did I use? L is 1 to k rho k. So the eigenvalues tell us how much information we retain. So we have our total amount, our total sum of squares, summing up the squared values of all of them. We split this up into two parts. The sum of square filled up by those eigenvalues which we use and those which we don't use. Because if we add up all the eigenvalues of this thing, L is 1 to n rho n, rho L, this is exactly the same as if we were to add up all the data matrices. You can see this here. This here is just the sum of all the square data elements in the data matrix. And that's what we get back if we use all the eigenvalues, because when we are in the full subspace, and I wonder if I'm missing no, I'm not missing a square here, I think. And so, this was my attempt to explain PCA. I hope it's halfway clear. I struggled a bit, to be honest, because when I tried to prepare this, I first tried to write down how I get to the matrix X. So how to make the rotation matrix and argue with that. But you notice the rotation matrix doesn't show up here. It is in here because it's formed by the U's. But you don't get we don't explicitly look at them when we look at this projection operator. And it's useful to not ask how much has U to be made in specifically, but only ask what subspace do we want to project in. Because I could, of course, use different rotation matrices. If I now have this rotation matrix and I multiply another matrix to that in order to change things in the subspace, as long as this is invertible, I don't lose any further information. So, I've written all this up here in case, is this the one? Yes, here this was my attempt to write all this up. Here you can also see again this decomposition in the part that we explain, in the part that we lose, so the reconstruction error. And if we now look at our data that we just had here, we can look at these eigenvalues because R actually reports the eigenvalues to us. Here, if you look at this PCA, you see it gives us here the rotation, the X matrix, and it also gives us a vector of eigenvalues. And well, actually, and from this we can see how much we have lost, how much we gain. And I can compare this now with the total. I think I have to multiply this times a PCA dollar because it's a standard deviation. We already divided it by n, the total number of variables. And so this is the actual thing. And if I add this all up, then you see this is the sum of my eigenvectors. And if I now look at how much do I get in this expression STDD, and I square this matrix and sum this all up, then we can see how much we have retained and how much we have lost. So it seems that our standard deviation, that our PCA retained 2% of the total variance, which is probably not that bad, given that we went down from 1,000 to only 20 dimensions. Actually, I would have expected that we retain a bit more, but my suspicion is that I'm missing a square here. I should have prepared this because I'm now not sure if I made this correct to multiply here with the total number of variances, so don't count on that. We probably should do this manually by looking at what happens if we calculate this eigendecomposition ourselves, which I've actually done down here. Where have I done this? The rotation, am I still in the right one? Here. Yes. Here. Okay. So what I done is we make here this YTY, which I always had, which is the expression vector multiplied by its transpose. On my blackboard, I always said transpose multiplied by the original matrix. Here, it's the original matrix multiplied by the transpose. That is for a subtle reason. There's a subtle disagreement between bioinformaticians and statisticians. Statisticians, whenever we write a data matrix, the individual observations or the units of observation, the objects, are written as rows, and the features that you measure are written as columns. Which probably makes sense that you say you write up what you measure for different columns, and then for each object that you measure, you add a row. But in bioinformatics, it's traditionally things are transposed, and you put the cells in the columns and the genes in the rows. This is not logical, but it stems back from the time when people had much more genes when they had samples. And so the mathematics is more realizable. This is why whenever you have biological data, the transpose is always the wrong way around. Now I do this, and I calculate here with this irrebar the first 20 eigenvectors. And if I look at this, it now gives me here the eigenvalues. Here are they actually. Let's see if this is now the same eigenvalues that I just tried to calculate here. And I put them here. Here 94,000. No, this is not. I know why. No, I still don't know why. I thought I would know. Okay, this PCA gives us this PCA function gives us this standard deviation function, which has something to do with the actual eigenvalues, but I can't remember if it's the square or the square root or multiplied or whatever. Probably it's the square root and multiplied by something strange. But what we now here have is these eigenvalues, and these eigenvalues, according to my logic, when I add them all up, dollar values, they should tell us how many squares we have here in total, and we can compare this now by the sum of squares that I get actually in the data. And we go down from 2.7 million to 340,000. So, but remember, lots of this variation that we have here is the Poisson noise that we want to get rid of anyway, which also brings us to the question of another way how we can look at this YTY, because it's a way to always explain PCA in a more hand-wavy way is that you say you try to explain the maximum variance, and in order to here, of course, you see what's meant by the maximum variance because we have centered our data, so that the mean of our data is 0. I should probably have also written this on my blackboard. The whole thing is centered so that for whenever I sum over all the genes, I get 0 if I sum over all the cells for a given gene. And that means if I want to calculate the variance of a gene over all the cells, I can simply take the square of this, because usually for the variance you have to subtract the mean before you take the squares, but the means are 0 all. So the variance of each gene is given by this thing here, only we don't divide by n-1. You might know this from ANOVA, where also we never do this division by n-1, but we just add up the squares and say, this is the sum of squares, we should divide it by n-1 to get the variance, but we stick to the sum of squares. And then we can say, this sum of squares is now split up into two halves, two parts, the sum of square which we retain the PCA and the sum of squares that we lose. And the sum of square is found again by the sum of the eigenvalues. And what I now wanted to show you as the last part is, right, it's useful to think a bit about what this YTY is. So YTY and if I look at this, so this is now, Y is a matrix of genes by, of cells by genes, exactly. These are the rows of cells by genes. So this is cell by gene value. Genes get index J. So I should write this as a JJ prime. So the element JJ prime of this matrix is the sum over all the cells of Y. The right thing is YIJ, and the left thing is Yij prime. And that, as you can see, is the covariance of the gene vector y.j and the vector y.j prime. Now I have a little notational thing because this is now not a feature vector, it's not a row of a matrix, but it's a column of a matrix. I try to make this clear by adding this little dot in front. So that's what YTY actually is. It's the variance covariance matrix from looking at the covariance of every gene with every other gene. And of course, in the diagonal, it has the variance of the genes. That's also why we reconstruct here with the eigenvectors the total variance, because the sum of the diagonal is the sum of the variances of a gene. That's the trace. And under rotation, the trace of a matrix doesn't change. So the total variance is the sum of the eigenvectors. Now, what else was it I wanted to say? And now you can imagine what our PCA is looking for. It's looking for genes which co-vary, which are strongly correlated with each other, and hence will be put to influence the same principal component. And this is how you then get this effect that if we had a two-dimensional data matrix where our data would look like this, and we look at the eigenelements of YTY, this would be the first eigenvector and this would be the second eigenvector, which is the usual way how it's usually depicted, that you say if your data is scattered somehow like this, then the longest direction of scatter is what you will get as the first eigenvector of this thing. And if you know a bit of mechanics, then you realize if you now say these dots are not data vectors, but they are point masses, and the whole thing is in this way making a rigid body, and we ask what's the inertial moments of these rigid bodies, then you know you also calculate the inertial tensor by constructing the eigenvalues. And the inertial tensor of such an object, that's exactly our quadratic form here. So, what else do we need to make us happy here? Short break. There's one little point which we haven't talked about yet, which is of semi-practical relevance. In a way, it's of big practical relevance, but in the other way, it isn't because it's been long solved. How do we actually calculate the eigenvectors and eigenvalues of such a large matrix like this one here, like this YTY? You've seen how I've done it. I just called this IRBA package. But of course, in this lecture, we wanted to get a bit in the details of how such magic actually happens and open the books of these black boxes. So how does the IRBA package actually work? So I can tell you that IRBA stands for iterated, restarted Lanczos-B diagonalization algorithm, named for some Hungarian mathematician called Lanczos, or I have no clue how to correctly pronounce him. And he suggested a way to do it which actually didn't quite work. And the IRBA experiment, and a lot of people then came up with the idea and said, yeah, the right idea, but there needs an extra component to fix it. And the one we are now using, this IRBA algorithm, is based on a on the implicitly restarted Lanczos-B diagonalization algorithm written by some guy called, what is this? IRBA. Yeah, by Baglama and Reichel, who, it's not that old, 2005 in the SIAM, that's this, in the SIAM journal, I think that's the Standard Numerics journal, and it's a bit involved, and I don't want to explain to you the IRBA algorithm. I once thought I've understood it, but it's probably, if you really want to dive into numerics, you want to know that. For us, let's do something slightly more, I'll do something slightly more modest. I'll tell you about how power methods work. The power method is the basic idea behind all these IRBA, Langkos, and so on methods. And the power method, we'll see in a moment, works sort of, but not quite, and then you need to come up with extra details to fix it. So it shows you the ideas, and then you have to work out the details. Or you don't have to work out the details because Langkos and Baglama and Reichel did that for us. And lots of other things, I think, in the 90s or so, probably about 1,000 PhD theses were written about how to properly work out these details. So, and the easiest thing we can do to work this out is the following. So first, first let's just double check that what our PCA gave us and what our eigendecomposition of YTY gave us is the same. So let's just compare the third principal component, and as you see, what the PCA function produced us as the third principal component. So this here was our first attempt. We asked the PCA function from this IRBA package to give us something, and then I used the partial eigendecomposition function of this thing to give us I either said, give me a PCA of a matrix Y, or give me a partial eigendecomposition of a matrix YTY. And as you can see, in both cases, we get the same eigenvectors. Here, this third eigenvector here, and the third eigenvector here, they are both the same thing. Actually, in case you want to compare it nicely, we do it like this, that where did it put this? Plot one against the other, and now, as you can see, they all sit like here. Now, power methods. How does this internally work? To do this, you can't read this here unless I render it. So I switch this over again and quickly show you how a power method works. How is this actually meant to be used? I think this way around. Been too long that I used a blackboard, and I forgot how to navigate with two blackboards. So let's say we want to find the eigendecomposition of some matrix M. And what we now do in the power method is something very simple. We first assume that the eigenbasis is U1 till UN, and of course with M on UL is lambda L UL. So this is the solution we are looking for. We don't know the solution yet, and we make a guess. Start with random. We start with some random vector V, which I just used random components, just drawn from the standard normal. And then what I now do is this random vector could in principle be decomposed. Could in principle, of course, decomposed in the eigenbasis. Of course, I don't know the decomposition, but there is a decomposition, which I don't know. And what now happens if I apply M on this vector V? Then you see what we will get is, of course, that each component gets multiplied by the corresponding eigenvalue. And what happens if I keep doing that? I apply M and M and M again and again. So I apply M, let's say, k times. Then what I get is lambda L to the k, VL, UL. And now you see what's happening. Imagine that these lambdas are all, again, sorted descendingly. Lambda 1 is the biggest, and the others get smaller. When this component, the component associated with the biggest eigenvalue, will grow much faster because of the power than all the other components. And you can imagine if I keep normalizing the vector after each thing, that when I get something which is, so if I take my m to be k, v, and I normalize this by dividing by its mean, then what I should get is something which is something like, let's say, now, this is now too. Well, you can imagine that this happens. Every time I apply it, and so my power method is simply I apply the matrix to a random vector. When I normalize the thing by dividing by its length, when I apply it again, when I normalize, apply it again, I normalize, and every time the component where it's collinear with the first eigenvector will blow up more strongly than the others. And after normalizing, I shrink all the others, and in the end, I should only be left with this one. And so, I've tried this out this morning, and it actually works. So I show you this. Here, I start with some random vector v. It's completely random, I just normalize it. And then I take here our matrix, y2y, and multiply it from the left against v. Now, R has the annoying habit that when you multiply a vector with a matrix, it changes our normal vector into a column vector. So I say here S vector to get a normal vector again, like this. And here is my, and I add it to this, and then here you see I calculate the norm of the vector. So I take my vector, I square it, I add up the squared components, I take the square root. So this is the norm of my vector, and if I divide it by this, now it has norm 1. And now, because we've already calculated the eigendecomposition of yty, I can simply take the result that I know I want to get at the end and plot it against the one which I have now. And what we then get is, let me show you, I first plot here my random vector. No, sorry, I should normalize it first. I take this, I plot my random vector, doesn't look at all. Now I apply yty once and plot it. And you see it's already slightly like this. Now I plot it yty twice. And already after 2 applications, we see quite a similarity between our random vector and the top eigenvector. 3, 4, 5, 6, 7, 8, 9, 10. Now after 10 iterations, it's really the top eigenvector, simply by applying the matrix 10 times onto vector, normalizing each time. The normalization is, of course, strictly not necessary, but it's useful because it allows you to get this in that way. And so I do this here, I plotted here the different things, and now I want to get the second highest eigenvector. So what do? Again, start with a random vector. I apply the vector, and now I don't want the top vector to amplify, so I subtract the top vector. So I project onto the top vector, the top eigenvector v1 that I've stored before and stored it here. And you see this is the projection in the direction of v1 of our first eigenvector that we got here. And I subtract this from my vector. And now the component for v1 is missing. And if I now normalize, then I will get only the second component to maximize. And in fact, if I plot this now against the second eigenvector, I already get a bit of correlation. And after a few more tries, here you see we are getting towards the second eigenvector. And again, I let this run over all 10 iterations, and we can see how with each time it gets a little bit closer. It doesn't really close up, 10 iterations wasn't enough that time, but still I use that what I now have here and add the third eigenvector. And for the third eigenvector, I do what I did before. I start with a random vector, I apply it once, I subtract the projection onto the first eigenvector and onto the second eigenvector, normalize, Ctrl Z, and plot. And again, if I do this, then with each time it gets a bit closer. You see this time I plot against the third eigenvector that I've calculated before. And so you see this primitive method actually works nicely to calculate an eigenvector. It's especially nice if our matrix is a sparse matrix, because then we can easily calculate this vector matrix multiplication quite fast. And that's also what this PCA-IRBA internally does. And yeah, but you can already see, even already with my third eigenvector, it converges slower and slower, and I get these things like this stuff here, which I don't really get rid of. You see, it doesn't line up perfectly, and that's what they mean by numerical instabilities. And that's the thing that can be solved now by improving on the thing, and why we have this better algorithms like this Langkos algorithm and this Baglama-Reichel-IRBA algorithm, which does a lot around that, but it takes a bit more. So, what was the last part I wanted to show you? Let's quickly go back to one more thing. Do I still find untitled pedestrian QMD? Is this here the right thing? I graph, neighborhood graph. Sorry, I got lost in my own many things, and I can't look at my figures of last time. This one is what I was looking for. So, okay, wouldn't have needed to read this again. I want to quickly run our usual standard thing, which we now often had. Again, our standard data set that we've always used. I think it's the same I now always did with my PCA on, but somehow I now read it again. Because I wanted to show you, have a look again at the PCA, or actually at the UMAP. But my computer is a bit slow, so give it a second. Come on. So, now we have our count metric. We calculate the fraction, the highly variable genes, and damn it, still slow. Maybe I've overloaded the my memory. The expression, let's do the PCA once more. Distance matrix and one more second. So I do my PCA, calculate the distances on this PCA, and then, why is this thing so slow? I only want to show you one plot, which should appear any moment here. Now it makes me here a distance matrix, which I don't need. Here. So this was our plot that we had last time, where we saw here our many 17,000 cells, or what it was, which are arranged like this. And I'm not sure if I showed you this sleepwalk tool. I think I showed it, where we can now see these individual cells, and whenever I put the mouse somewhere, you can see where the PCA, what the PCA distance in the cells are. And you can see the imperfections of this UMAC thing, like that. You see these all are similar, but this thing here seems to be quite different, even though it's plotted here. You see nothing lights up as close neighbors. Here a bit more, but what you can also see is that there's a gradual transition here along this. If I plot, I can always go from one to the next, and so on. And what I now want to do is, and what I can now imagine is that this is what we did last time, that we split this into clusters with Louvain, is maybe not that helpful. You remember we used colors and said this one color with the next color with the third color, and it made more or less arbitrary boundaries. But it might make more sense to look at this thing as a continuum that starts here and runs along here and ends here. And for this, we want to assign to every cell a number, which tells us how far it is along this trajectory. We might say this here is the number, actually, which one was the start? I think this was the start and this was the end. So let's say this is the number 0, and then it comes 0.1, 0.2, 0.3, 0.4, 0.5, and here is when 1.0 is the end. And for this, we somehow need to find a way through this. And we call this a pseudotime, which gives to each cell a number like that. And I want to show you in the next lecture 2 ways to do that, and then what we do mathematically with this. The first thing is called a principal curve, and in it fits nicely because it expands on this idea of a principal component analysis. So imagine you have a data vector. Now let's imagine our PCA space were 2-dimensional, so that it's easier to see. And we have a point sitting in some kind of banana-like stuff, like this here. And now, if I were to do a PCA on that, probably my top principal component would go in this direction. But what I can now also try to find is a curve. Let's imagine we find a curve like this here. And this curve we call is now the curve, the optimal curve, such that if we project each cell onto this curve, our projection loss, so the sum of all these squared residuals, is as small as possible. And you can imagine the curve has to go for this. If I make my curve somehow differently, then this is harder. Now I need to have some extra constraints, because if I just tell you, find a curve that minimizes the projection loss, then you will come up into this here. And if it goes to all the points, then of course the projection loss is 0. So we have to impose a minimal stiffness and say this curve shouldn't wiggle too much. And there's different ways. One way is a penalty. For example, that we say the thing that we want to minimize is, so if this is our curve, let's call it gamma, and this here is gamma of 0, and this, let's say, is gamma of 1. And this here are our data points, yi. Gamma is also a vector-valued curve. Then, of course, every yi now gets a pseudotime, which is the projection onto the curve. So ti is the curve point where it is closest, the point on the curve where it is closest on this thing here. And in that case, if I have a curve, I can assign to each point a pseudotime by saying, what's the closest point of a curve? Take the parameter value of the curve parameter at this point and say, this is this point, this cell's pseudotime value. And then this cell gets 0, and this cell gets 0.5, and this cell gets 1. And on the other hand, once I have fixed these TIs, I can make my pseudotime curve by saying, so this is my the fixed pseudotimes. is this here, and then fixed curve, where we say we take a curve and let me see, we check again this here for each cell yi minus now the curve point at this curve's pseudotime. And now we say we want to minimize this here summed over all I squared. And we want to find the curve that minimizes this. So we take some function space of possible curves and choose in this function space the function that minimizes the sum of squares. And one thing that we might do is that we take all continuous curves, and just to make sure that the thing doesn't cheat, by being too wiggly, we might add a penalty like 0 to 1, which penalizes the second derivative so that it doesn't get too much curvature. We integrate the second derivative or the absolute value of the second derivative along this whole curve, and say if this becomes too big, then not plus. When this is not, so our curve needs to not only minimize the sum of squares, but it also needs to minimize this thing. And this alpha parameter now gives us some means on how much wiggling is allowed. Another possibility is to not use that, but instead use a function space that doesn't contain two wiggly curves. And what we will use for that point is called a spline basis, where we say the individual components of this, so the x component and the y component of this curve needs to come from a function space where each function is made up from a spline basis. Spline basis looks like this. So you have a couple of basis functions which sort of peak at different places and which have a value, and you can now form new functions by taking linear combinations of these basis functions. And you use one such function to make your x coordinate and one to make your y coordinate for the gamma, and this can't wiggle too much because they don't give you enough chance to wiggle. And a third possibility is to use the so-called local regression, which is also a popular way to do smoothing. Overall, the whole thing runs under this term smoothing, where we have points and we have to draw a smooth curve through the points, and it should be smooth not only in the sense that it's continuous and has, in mathematics, the term smooth means or we have infinitely many derivatives and it's infinitely differentiable, but here we mean by smooth in a more general sense. It shouldn't wiggle too much. And I want to show you 3 different ways of how to make such curves smooth, because we will need smoothing for 2 reasons. First, to make this pseudotime, and second, we will need it for something else. And actually, we will turn the things around. I will show you the second part first. Imagine we already have a pseudotime. And what we can do is that we take one specific gene, and here the pseudotime, and then for each cell, we look at the expression of this gene along this pseudotime. And then, of course, we want to smooth this as well, because then we can give a nice feeling of saying in which order do the genes change along this trajectory, which genes change first, which genes change later, which is, of course, what we need in order to make biological conclusions of that. And yeah, so plan for next week or for next Monday is, I think, a holiday, right? Then plan for whenever it's not a holiday is we will talk about how to do some smoothing. And we will do this using first a least square criterion and then a likelihood-based criterion, and then we will use this also to make our curves. And we will make some nice plots which probably will look like actual biology. So, okay, now 17:23. Now I have nearly talked for 90 minutes, so probably that's enough. What else was there? Right, on Wednesday, I wanted to finish our Leiden implementation, our implementation of a Louvain clustering, Louvain or whatever we started. And we will, in that case, what we will hopefully do on Wednesday is that we first optimize the algorithm by using these local updates, which will speed up stuff dramatically. And then we will also optimize the platform by switching from interpreted Python to compiled numerical Python, and then we should get a nice fast algorithm which gives you a typical thing how you actually implement complex numerical algorithm in practice so that they actually run fast enough to be usable. At least I hope it will turn out to be fast enough because I haven't tried it myself yet. And then another time, the next thing what I've just already sort of gave you as a teaser about this curve fitting, that's also something I want to do numerically, that we implement this ourselves, this iterative procedure that I've just mentioned here, where we always go between minimizing this and minimizing that and changing back and forth. And so, of course, we have to implement these two optimization algorithms. Yeah, and maybe the last thing on my list of how far I've planned ahead so far is that we will also look at this last second dimensional reduction where we go from PCA space to this UMAP thing and try to implement a slightly simplified version of such an algorithm by maybe we manage to get a t-SNE to write ourselves. Okay, that's what I have for today. And then see you on Wednesday, those who are up to some programming, and the rest see you next week.